sleep so you don't talk.
I woke up just for this.
Woke up just in time. Professor Lee would now like to make an announcement.
Now the reception will be held at the downstairs of this building, which is located by 2 stories below of this level. The reception will be held right after.
I'd like to make one announcement too. I'd like all of the U.S. delegates to wait for about
How to operate? I can take.
Well, it's time to begin this morning's session. The first presentation is different than from the schedule. As you remember, it was switched from yesterday. The presentation will be given by Professor Levi Thompson, University of Michigan. He received his bachelor's degree at the University of Delaware, a PhD at the University of Michigan. He is currently on the faculty at the University of Michigan and has been there since 1988. Professor Thompson.
Thank you. Morning. Can everybody, I presume you can hear me. I feel like a celebrity. Let me thank the organizers for their kind invitation. I also want to acknowledge that this is truly a collaboration of scientists from the United States and those from Korea. Jung-gil Choi, as a matter of fact, is a graduate of Seoul National University, and Hyuk-Jun Lee is also a Seoul National University graduate. It's also important to recognize that this work is funded by the National Science Foundation, who I think co-sponsors this workshop. In addition, Chevron Oil Company and Union Carbide Corporation. Okay, the motivation for this work is basically twofold. Several years ago, as a matter of fact, maybe 10 years ago now, Boudard's group discovered that you could create high surface area materials, non-oxide materials, using a technique called temperature program reaction. Basically, you heat a precursor up. In this case, it's an oxide precursor. Heat that up in the presence of either ammonia or some carbonaceous species. And what happens is you convert that low surface area oxide into a very high surface area material. This is of obvious importance in catalysis, and there are a number of other areas where high surface area materials or nanostructured materials may also be important. But the bottom line is that you create these high surface area materials. They may be used as supports, or as I'll show you in this talk, they can also be used as catalytic materials. This is not the first work in the area. There have been a number of efforts to try and nail down what types of catalysis can be carried out over nitrides and carbides. For example, and I'll suggest that nitrogen-nitrogen bond activation in the form of ammonia synthesis has been carried out by Volpe and Boudard some 7 years ago. You can also do three-way catalysis over carbides, CO hydrogenation, thanks to Professor Bell's group. Of particular importance in this work is hydrodenitrogenation, CN bond activation, which was, to the best of my knowledge, first demonstrated by Schlater et al. And then finally, you can also do dehydrogenation reactions. As I mentioned, I'll focus my talk on hydrodenitrogenation, which in some respects is an environmental catalysis reaction. I'll use that right now, as this, I believe, is an environmental catalysis section. This talk will be broken up into 4 different areas. I'll talk briefly about the factors that we've discovered influence the structure of bulk molybdenum nitrides. We'll also talk about some of their catalytic properties and how structure and function relate for bulk materials, and we'll use HDN again as the test reaction. We'll look at some of the surface properties of these bulk nitrides, and then finally some more recent work that we've just completed, where we've evaluated the surface properties of a series of molybdenum nitride films. That part is not covered in the abstract, so you may want to pay particular attention to that. And if you're interested, we're preparing a manuscript. If you let me know, I can send you a copy. A particularly complicating issue related to nitrides, molybdenum nitrides in particular here, is that they can exist in several different structures. Displayed here is an illustration of the major structures, the equilibrium structures that molybdenum and nitrogen can exist in. We all know that the molybdenum metal lattice is body-center cubic. Adding nitrogen, in this case, the nitrogen resides at interstitial sites. We call these materials interstitial compounds. Addition of a nitrogen converts this BCC structure to a BC, body-center tetragonal structure. Increase in the nitrogen content, you can create an FCC structure, and then finally a hexagonal structure. The important issue here is that these are interstitial compounds. They can dissolve varying amounts of nitrogen. The lattice structure is not necessarily dictated by the nitrogen to moly ratio, although there are some limits if we look in the phase diagram for these structures. So it's not only important for us to determine what the lattice is, but it's important from a catalysis standpoint to also know what the nitrogen to moly ratio is. And as it turns out, the Hogg rule, which governs whether or not a non-metal atom will dissolve into this lattice, suggests that carbon, oxygen, and several other elements can also exist in a lattice, so we need to be mindful of that, and if available, use tools to try and determine what the carbon content is in addition to the nitrogen content. When we set out, when we started this research, we decided that we wanted to try and do rational synthesis of these materials, see if we can control the structural properties first, and then, if that was possible, see if we could control the catalytic properties. There was some work done by Jaegers et al., which suggested that there was a series of reactions through which moly trioxide is converted to either oxides or the nitride. And because these are parallel pathways, like other homogeneous reactions, we expected that the temperature at which the reaction is carried out, in addition to the heating rate that is used in converting the oxide into the nitride, would help us control the selectivity to product. You'll notice that there are three regimes. There's this red regime here, during which moly trioxide in the presence of ammonia is converted into an oxynitride and dioxide. Subsequently, and it's kind of hard to see, but the oxynitride can be converted into the nitride at temperatures between about 500 and 600 degrees C. The dioxide can then convert into the gamma phase of the nitride or the delta phase of the nitride. You'll remember that the gamma phase is FCC and the delta phase is hexagonal. Believing that we could control the selectivity and perhaps the structure of the materials by controlling the heating rate, you'll notice that we employed two different heating schedules. We have heated from about 350 to 450 using beta 1, in this case beta 1 being either 40 K per hour or 100 K per hour. We've used a second heating interval from about 450 to 700 degrees C, and here we used either 100 K per hour or 200 K per hour. Again, we were trying to control the structure of the materials, and in the worst case, see if there was an influence of the first or second heating rate on the structural properties of the materials that were produced. In addition to the heating rate, like most other reactions, the space velocity is also important. Here we have listed the experimental parameters that were used. We used a 2k factorial experimental design to try and guide our experiments. 2 levels, as I mentioned, for beta 1, 2 levels for beta 2, 200 and 100, and then 2 levels for the space velocity. These by no means bracket all of the conditions that were used in either our lab or in other labs to try and create these materials. However, it does allow us to determine in a very efficient manner whether any of these 3 parameters has an influence on the structural properties, and then I'll show you whether those structural properties have any bearing on the catalytic properties. You'll notice that, for example, when comparing 1 and 2, the only difference between the 2 of those experiments was the first heating rate that was employed. So this experiment would allow us to determine whether the first heating rate has an impact on the structural properties of the material. Comparing 1 and 3, we can look at the influence of beta 2, and then 1 and 5, we can look at the influence of the space velocity. This is the simplest treatment of this data. There are statistical analysis packages that will allow us to, with a 2k factorial design, determine coefficients or correlation coefficients for these results, and we use those as opposed to simple comparisons with only one parameter varied. What we find is that, and you can see to some extent based on the surface area that we list here, that there are very significant influences of beta 1, beta 2, and the space velocity on the structural properties of the material. When we do the statistical analysis, we find that individually the space velocity has the most significant influence on the ability to produce high surface area materials. Again, you'll notice that, for example, if we take sample number 2 and compare that to sample number 6, simply changing the space velocity has caused a very significant increase in the surface area of the material. Combined, beta 1 and beta 2 also have an influence. And when I say combined, we look at the value of beta 1 and beta 2 together as opposed to the values individually to try and determine what influence it has on the structural properties of the material. Some of that information is listed in the abstract, and I won't go into great detail on that, but just recognize that there is a broad variation in the surface area as a consequence of the synthesis parameters that were employed. Please remember that sample number 2 has the highest surface area, 116 square meters per gram. Sample number 8 has the lowest surface area, 4 square meters per gram. Throughout this part of this talk, we will make comparisons between these 2 materials. And let me also mention that we could categorize these materials as being low surface area, medium surface area, or high surface area, and you see the ranges that we use in this particular work. The results of the experiments that I just discussed and some additional experiments using in situ X-ray diffraction and thermogravimetric analysis has led us to believe that there are a series of parallel pathways that occur during the nitridation of molybdenum trioxide. What's important here for this particular talk is not the individual species that are created, but the surface areas that you can produce. All of the materials in our case are predominantly this gamma dimolybdenum nitride. We see no evidence of the delta phase in any of the experiments that we've carried out. You'll notice that apparently things that go through this dioxide produce either medium or low surface area materials, while pathways that go through this bronze produce higher surface area materials. And we believe that that's one of the keys, that and the structural character of the reactions that take place dictates whether we can create high surface area materials or not. For those of you who are familiar with the concept of topotacticity, apparently topotacticity combined with pseudomorphic reactions are what gives rise to these high surface area materials. In terms of catalytic properties, we find that they're very active for hydrodenitrogenation. They're competitively active with most commercial HDN, HDS catalysts, which is very intriguing. This talk will only focus, it will not deal with any of those types of comparisons. We will only compare the structural properties of molybdenum nitrides with their catalytic properties. What we notice is that on a surface area basis, the activity appears to decrease with increasing surface area. This is a classic example of structural sensitivity. As you remember, molybdenum nitride is very much like an alloy in the sense that it has two different elements. So we not only have to be aware of what the structure is, what the bulk structure is, but we also need to be aware of the composition. And so what we'd like to do is try and compare the catalytic properties with both structural and compositional characteristics. And this slide summarizes that. I've listed the results in order of activity here based on oxygen uptake, starting with sample number 2, which has the lowest activity, going to sample number 8, which has the highest activity. You'll remember that number 2 is the highest surface area material, while sample number 8 is the lowest surface area material. Convert those surface areas into particle sizes, and we find that there is more or less a monotonic increase in the activity with an increase in the particle size. As we increase the particle size, you can see more or less that the activity increases. And this is a somewhat significant increase in activity, certainly outside of the experimental error that's expected for these, for the reaction rate measurements or the particle size measurements. As I mentioned, we also need to be aware of what the nitrogen to moly ratio is. You'll notice that there is not a clear correlation between nitrogen to moly ratio and the catalytic activity. One note that we should make is that the sample here with the larger particle sizes, it appears that nitrogen to moly ratios near 1 produce the higher activity materials. And as I'll show you in a few minutes, we believe that's because of the presence of the delta phase near the surface. As far as the structure of these bulk materials is concerned, we use high-resolution electron microscopy, and this is an example. Actually, this is the real micrograph, and we can do diffraction on selected areas. We could also digitize these images, which is a much more efficient way to handle them. We digitize, and then we can select the region here, for example, do the mathematical equivalent of a diffraction, and get a diffraction pattern which can be indexed to determine what the lattice constant and the structure of this material is. And as I'll show you, these are the lattice constants that we calculate. We can either fit these to a face-centered structure or to a body-centered structure. We find that the body-centered structures are self-consistent and with respect to several different zone axes, and so we believe that it is in fact near the surface a body-centered structure. You remember that the bulk is FCC. This suggests that the bulk and surface structures are very different. The lattice constants that are listed here are bracketed by those of the equilibrium body-centered structures, moly, which is BCC, and then this beta phase, which is body-centered tetragonal. This might suggest that, well, obviously the lattice structure or the lattice constant is varying while the structure remains constant, but it also may be an indication that the nitrogen to molybdenum content has caused some change in the lattice constant of the structure. And this is not unexpected. As we increase the amount of nitrogen in the lattice, we should expect that the lattice will expand. To summarize briefly this first part, we find that there is there's clear evidence that the bulk structure is the FCC molybdenum nitride. The surface structure is body-centered tetragonal. Body-centered. It's possible that it's molybdenum or this beta molybdenum nitride. The surface stoichiometry of the most interesting materials appears to be have a nitrogen to moly ratio of about 1, which suggests that perhaps if we were trying to align this with the equilibrium structure, perhaps it's the delta phase. This is a schematic to kind of illustrate that. It also helps us jump into the next part of this talk. What we, under ideal circumstances, would like to do is take these individual phases where we can control the structure and the composition, and then look at the catalytic properties of those, independent of, or with materials that are phase pure, and we don't have to worry about, for example, the presence of the beta phase when we're trying to determine what the catalytic properties of the gamma phase are. And so we decided to use thin films for this part of the work. Those of you who are familiar with nitride and carbide catalysis, or the synthesis of molybdenum nitrides and carbides, will recognize that it's not an easy task to create phase pure materials. Here we use a technique called ion beam assisted deposition. It basically allows us to co-deposit the atoms of interest. In this case, we co-deposit molybdenum atoms while we simultaneously bombard the surface with low energy nitrogen ions. The bottom line is that we can control the stoichiometry, and by controlling the stoichiometry, we can in some cases control the structure, as I'll show you on the next slide. There is a strong correlation between here the film composition, which is determined using Rutherford backscattering spectrometry, and the arrival rate ratio, which is basically the flux of nitrogen ions over the flux of molybdenum atoms. And you can see that there is a more or less linear relationship between the two of those. As you might expect, there are cases where we can produce phase pure materials, and those are highlighted. In this case, we have a phase pure gamma film. The blue indicates a phase pure beta film. In between, we have mixtures of the two. Purple is a phase pure delta film. Again, in between, we have mixtures of the delta and the beta phase. For the purposes of this talk, it's important that we can produce phase pure materials. We take these films and then we have characterized their structure and composition, and we also look at their surface characteristics. Let me show you that just to indicate that these are phase pure by X-ray diffraction. We do elemental analysis again by Rutherford, and we can also do electron microprobe analysis to see if the lateral composition is relatively uniform. As it turns out, temperature programmed desorption, in this case of hydrogen, ends up being a very useful tool for determining the surface characteristics. This is a TPD spectrum for one of the bulk nitrides. It's got a nominal surface area of about 24 square meters per gram. You'll notice that as we increase the flow rate, and these are carried out in sort of the traditional, conventional way that you would do temperature programmed desorption. We absorb hydrogen and then heat the sample up and look at how hydrogen desorbs. You'll notice that the character of the spectrum changes as we increase either the flow rate or the heating rate. This is indicative of the presence of a subsurface site, and for those of you who are interested, there is literature in this area by Leary et al. That suggests that if the intensity ratios change with either heating rate or space velocity, then that is a clue that you potentially have subsurface sites. Based on these results, we would conclude that there are two surface sites, this low temperature surface site and then the smaller peak here, and there is a subsurface species which is highlighted in blue. That seems to decrease with increasing flow rate. It also changes dramatically with increases or changes in the heating rate. The sample I just showed you was sample number 1, a kind of modest surface area material. This is sample number 8, which, as you'll remember, had the lowest surface area. It also had the highest intrinsic activity. We notice that there is a very marked difference between the TPD spectrum for the higher surface area materials and that of this low surface area material, we were struck by the differences, and as I'll show you on the summary slide, sample number 8 was the only one that gave rise to a single peak in the TPD spectrum. You'll notice here that I've given temperatures for both the low temperature surface and the high temperature surface sites. In addition, we have the subsurface site listed here. Relative activities are also given. The highest activity material, as I mentioned, has the presence of a single surface site. When we now take a look at some of these phase pure thin films, and this is just an example, the beta film, if we do hydrogen TPD, and this is all in a UHB system, you notice that there are 2 peaks. As we increase the dose, the centroid of this peak here does not change. That's characteristic of a first order desorption process. The gamma film, very similar characteristics. We have 2 peaks, a low temperature and a high temperature peak. Again, as we increase the dose, the centroids of the peaks do not change significantly. You'll remember that many of the materials of the bulk materials that we looked at had 2 peaks. Interestingly, the delta film, in the temperature range of about 300 to 900 degrees Kelvin, appears to only give rise to one TPD peak. And we believe that, as you'll remember, that is one of the reasons why sample number 8 is so much different from the other samples. Let me just skip a few of these. When we change the heating rate, and let's just focus on the spectra at the top. When we change the heating rate, we notice that, for example, in going from about 6 to near 10 K per second, you lose this second species here. That suggests that it's a subsurface site. We see subsurface sites with both the beta and the gamma films. We do not, however, see any evidence of subsurface sites with the delta film. Let me just conclude by saying that, as I've gone throughout, this is basically what we see. What's important here is that I think we've identified what makes sample number 8, or this low surface area material, so much different from any of the other samples. You remember that the nitrogen to molybdenum ratio was near 1. In the passivated form, and I should have mentioned that immediately following synthesis we passivate the samples. So there is the presence of ammonia at the surface. We do a reduction, and the results that I showed you, the nitrogen to moly ratios, are those of the reduced material. So we've removed all of the adsorbed ammonia and anything else, free nitrogen, if you will, that's on the surface of the material. So those, I think, are more characteristic of what the material is and not what's on the surface of the material.
I think maybe we can close our discussion here.